Welcome back to linear algebra. In this video, we're going to be going into inverse linear transformations. Remember that in essence, linear transformations are just functions. Specifically, they are functions that work on vector spaces, and they are functions that have a certain behavior around linear combinations, but they are all functions. And so a lot of the ideas that we've talked about in previous mathematics courses on behavior you care about with functions comes up again as behavior we care about for linear transformations. Key here today are the ideas of function composition, right? For two functions, f composed with g, evaluated at some point f, at some point x, is the function f evaluated at the point g of x. And inverse functions. F and f inverse are defined such that f composed with f inverse evaluated at x just gives you x, or equivalently, the way you see it written more often, f of f inverse of x is equal to x, and f inverse of f of x is equal to x. And when we talk about inverse functions, the question when and where is the inverse defined? How do you know that the inverse will be defined? Is always an interesting question. And the answer that you learned in algebra, in your college algebra or high school algebra coursework, is the horizontal line test. If you have a curve that looks like this, each horizontal line passes through the curve at most once. This is an invertible function. If you have a function that looks more like this, there's a horizontal line which passes through the curve more than once. So that's not an invertible function. Great. Those are the ideas that you should be familiar with thinking about functions, specifically thinking about real valued functions of one real variable, the types of functions you worked with in high school algebra and in college algebra and in calculus. In this course, we want to look at transformations, but we want to look at those same kinds of questions. So let's start with composition. And immediately we get hit with something that rarely comes up dealing with real valued functions. And that is ensuring that we have the right sort of thing. In real valued functions, it can happen sometimes, right? If one of your functions is a square root function, you have to make sure that your other function is giving you a value out where when you take the square root, you're not going to be taking the square root of a negative number. But in linear transformations, it becomes a much bigger idea because your linear transformation is going to take in a vector in one vector space, in one size dimension, and spit out a vector in a different dimension. And so if you have a linear transformation that takes three-dimensional vectors and turns them into two-dimensional vectors, and you have a linear transformation that takes 5-dimensional vectors and turns them into 3-dimensional vectors, well, the composition will work in one direction, but not in the other, right? If we get out a 3-dimensional vector and put that into the other function, we're in good shape. If we get out a 2-dimensional vector and put it where something is expecting a 5-dimensional vector, we're completely out of luck. It doesn't work. And so right away, we need to have care taken. Let's take one linear function. I'll call it L1, which is going to go from Rn to Rm. And let's take another linear transformation. Let's call it L2, which is going to go from Rm to Rp. L2 composed with L1 is perfectly fine. It's going to go, well, L1 is going to take on a vector in Rn. It's going to produce a vector in Rm, which is then going to be fed immediately into L2 and give us a vector in Rp. But in the other order, L1 composed with L2 is not defined. Because if we evaluate this, we would evaluate L2, which would take in an m-dimensional vector and then give us a p-dimensional vector. And then we try to feed that p-dimensional vector into L1, which is expecting an n-dimensional vector. And if p and n are two different numbers, that doesn't work. You can't take a vector of the wrong dimensions and put it into a linear transformation. All right, so a quick theorem here. When defined, the composition of two linear transformations is also a linear transformation. And the proof of this is, as has been the case in many of the proofs we've done recently, the proof is more interesting than the theorem. So to see how this works, let's take a couple of linear transformations, L1 from Rn to Rm, and L2 from Rm to Rp. Let's let both of these be linear. Right? Again, linear transformation is something we care about. Now, one of the things we know about a linear transformation is that we can always represent a linear transformation as matrix multiplication. And that's going to be key for this particular proof. So I'm going to set up very specifically that these transformations are defined by matrix multiplication. And notice the way we set this up. I can define for some vector v in Rn, I can define L2 composed with L1 acting on V, but the transformation, the composition is not defined in the other order. What we talked about before, I used the same vector spaces as we did in the last one. All right. Setting up this composition, as we saw with real variables, this is L2 evaluated at L1 of V. And of course, we know that L1 of V is A times V. And we know that L2 of something is B times that something. For the next step, remember at this point that we have a bunch of matrix multiplication. B is a matrix, A is a matrix, and V is a vector, which is just a one column matrix. So using the associative property of matrix multiplication, I can rewrite that instead of B times AV, it's B times A multiplied by V. And whatever B and A are, the important thing is that B times A is a matrix. And so this composition, L1, L2 composed with L1, acting on V, is the same thing as multiplying the matrix BA times V. Or to put that a little bit more generally, we can represent the transformation L2 composed with L1 as multiplication with matrix BA. And because we can represent it as multiplication with a matrix, it is linear. Any transformation which can be represented as matrix multiplication is a linear transformation. Any linear transformation can be represented as matrix multiplication. All right, so the idea of function composition has translated nicely to transformations. We can compose two transformations. We see that whenever we compose two linear transformations, it's the product of some matrices. And with the idea of composition in hand, we can turn our attention to the idea of the inverse of a transformation. All right. So it's been a while since I've used this symbol. The backwards looking E here is read as there exists. Right? So transformation L is invertible if and only if there exists an inverse transformation L inverse such that L composed with L inverse acting on V is equal to V, and L inverse composed with L acting on V is equal to V as well. Technically speaking, we can have this occur for any dimensions input and output. For the sake of practicality, for the sake of making things simpler to use, let's focus on linear operators. Remember that linear operators are linear transformations for which the domain and the codomain are the same vector space, which I'm going to represent as Rn. And as always, whenever we have a linear operator, a linear transformation, we can represent it as multiplying by a matrix. And that takes us to the theorem that is going to be the heart of what we're looking at in this video. The inverse transformation for a linear operator is represented by its inverse matrix. So when we have linear operator L represented by matrix A, the inverse linear operator is going to be represented by matrix A inverse. And a natural corollary that will fall from this, I'm probably not going to take the time to write it down, that a operator is invertible if and only if its matrix representation has an inverse matrix. So we tie back to that question we've been asking since we started talking about matrices. How do we know when a matrix has an inverse? Now the question is the same as how do we know when a linear operator has an inverse transformation? All right, but let's get through this theorem first. The proof is fairly natural. Right? Consider operator L represented by invertible matrix A. Well, the definition of the inverse matrix, A times A inverse is the identity matrix I, and I times anything is that thing. Or A inverse times A is also the identity matrix, and identity matrix times V is V. All right. So if we define L negative 1 of V, L inverse of V, as A inverse times V, then L inverse composed with L acting on V is A inverse times AV, which is A inverse times A times V, which is just V, and we can do it the other way. I'm not going to write out both sides of the argument. All right, that's half of the battle. If you have an invertible matrix, then the inverse matrix gives you the inverse transformation. What if we took it a little bit further back? Consider an arbitrary linear operator L, which has an inverse transformation L inverse, and we have a different matrix, I'll call it B, which represents L inverse. Then L inverse composed with L acting on matrix V, or matrix L inverse composed with L acting on vector V is the same thing as matrix B multiplied by matrix AV. And we can regroup that as B times A times V. And we know that that has to be equal to V. The only way for B times A multiplied by vector V to be equal to V is if B times A is the identity matrix. And similarly, A times B must also be the identity matrix. And thus we have shown that A is an invertible matrix and that B is the inverse of that matrix. All right. So again, the big takeaway from all of this, the inverse of a linear transformation is also a linear transformation, and the inverse of a linear transformation is equivalent to the inverse of the matrix that represents the transformation, assuming you have a square matrix. When you have a transformation that is not a linear operator, some other weird things can come into play. We don't want to deal with them. It just is complication for the sake of complication. Up next, we want to start looking into when and how can we identify that a matrix is invertible. And we're going to use a lot of the tools that we built up talking about the range of a linear operator and talking about vector subspaces in general as a way of getting there. Right. The big key here, thinking back to what we've talked about with functions in general, a function has an inverse if it passes the horizontal line test, if there is no output value that shows up in multiple places. Figuring out in general all of the possible output values that show up in multiple places is a bit of an ask when it comes to linear transformations, because instead of having the one dimension, you have n different dimensions that you're trying to graph, and visualizing that is literal headache inducing. Luckily, we can actually restrict that a little bit. It turns out that if there are output values that are duplicated in a linear transformation, that the zero vector is going to be one of them. Doesn't have to be the only one, but it is going to be one of them, and that's good enough for us. And so, instead of looking at the output, the range of the transformation in general, the null space of a linear transformation is the set of all vectors such that the transformation on that vector gives you the zero vector. And I did define this for a linear transformation in general, just to emphasize that my vectors are coming out of the domain, not out of the codomain, right? 0 is, I wanted to highlight that in the other color, 0 is the vector that is in the range, in the codomain. V is a vector in the domain. All right. A very quick theorem here. Let's consider a linear transformation L represented by matrix A. And notice that the null space of L is the solution set for the homogeneous system AX equals 0. Right? That falls almost directly out of the definition. Right? The null set of L is the set of all vectors so that L of V is 0. And since L is represented by A, L of V is the same thing as A times V. Right? So using V or using X doesn't really matter. It's an arbitrary vector, and it's the collection of all the vectors that satisfy that. All right, so I'm going to state that. I'm not going to write down the proof. I hope that you can see that proof without writing it down. But if you can't, take a couple of minutes, write it down, make sure that it makes sense. My second theorem, same premise. We have a linear transformation L, which is going from Rn to Rm. The null space of this transformation is a vector space. It's a subspace of Rn. This does take a little bit of proof. We showed in a previous video that L of 0 has to be equal to 0. You can do that by the linearity, right? 0 times any vector is the 0 vector. So take any vector, multiply by 0. It's the same thing as multiplying 0 by whatever result you get out, which is always the 0 vector. Right? So the 0 vector is in the null space. That's important. And then we also have to show that the null space is closed under linear combinations. So take two vectors in the null space, take two constants, and then operate L on C1v1 plus C2v2. Using the fact that L is linear, this is going to be C1 times L acting on V1 plus C2 times L acting on V2. I'll mark that down since L is linear. And then again, because V1 and V2 are in the null space, L of V1 is 0. And L of V2 is also 0. Right? That's the definition of the null space. We said that V1 and V2 were in the null space. That means that when we take the operator, we get the 0 vector out. something times the zero vector is the zero vector. Adding the zero vectors together is the zero vector. And so by definition, this linear combination, C1v1 plus C2v2, is also something in the null space of L. Right? That's what it takes. The zero vector is in the null space. The null space is closed under linear combinations. The null space is a vector space. And a nice follow-up to that, of course, since the null space is equivalent to the solution set of the homogeneous linear system, that means that the solution set to any homogeneous linear system is also a vector space. Nice. All right. How do we use that to our advantage? Well, again, what are we looking at? We want the matrix or the linear operator to be invertible. We want the matrix to be invertible. And we know that a function cannot be invertible if there are multiple input values, multiple values from the domain that map to the same output value. The null space is a collection of vectors that all map to the same output value, the zero vector. And so if there's more than one thing in the null space, then we're in some trouble. So a bit of an aside, but very important for what we're looking at. We know that the zero vector is in the null space. And it looks like our plan, our drive here, is to show that the zero vector is the only vector in the null space. And so it's worth analyzing the set that has just the zero vector in it. I claim here that it is the vector space with dimension 0. Well, that's kind of a theorem, but also mostly a postulate because it's kind of vacuous. Remember that the dimension of a vector space is the number of vectors that you have to have in the basis in order to get the span to be everything there. Well, what does it take to get a span that is the zero vector? Your basis vector is the zero vector, but the zero vector is not linearly independent even of itself. So your basis set is the empty set. All right. It makes sense, I hope, right? The span of the zero vector is the zero vector, but the definition of linearly independent is if you take a linear combination, the only way to get the zero vector out is for the constant to be 0. But c times 0 is equal to 0 for all c, which means that 0 is not an element of the basis for the zero vector because it's not linearly independent. So we're kind of out of ideas, and with nothing else to do, we decide to define the basis of the vector space containing just 0 is the empty set. And the span of the empty set is going to be the set containing 0. Right? Kind of an odd thing to work with. It feels like it works. I hope that's not quite a proof. It may not be convincing, but hopefully it mostly makes sense. So we can go with that. And as I'm writing this down, I realize I forgot to include a definition that is very important to understanding and being able to read this lemma. The nullity of L is the dimension of the null space of L. And then I have a lemma here, which says that the rank of L plus the nullity of L is equal to N. And I can play around a little bit with the proof of this, but I want you to just consider a matrix in reduced row echelon form. In reduced row echelon form, you have some non-zero entries, or some non-zero rows. And we know that each of the non-zero rows contributes to the row space, and the rank of the matrix, the rank of the operator, is the number of non-zero rows. I don't quite have enough time to really prove this. I'm not really interested in finding enough time to prove this. But the number of zero rows here is the nullity. Although I suppose it actually makes a little bit more sense with the columns. The vector space that we are looking at here, you can either have something happen with that vector or not. And component by component, the components of a vector which give you something out of this are going to correspond to the rows that are in the row space, and the components of the vector that don't are going to correspond to the empty spaces, the zero spaces, which I'm now labeling as the null space. And very clearly, the number of rows that have non-zero entries and the number of rows that have zero entries must be the total number of rows in the matrix N. All right. So again, not quite a proof, but hopefully something that gives you some feeling of justification for this lemma. There is a more formal proof listed out in the textbook. If you're interested in reading it, I encourage you to do so. If you're not interested in reading it, don't worry about it. I don't think there's anything valuable in that proof, at least as far as what we're going to be working with this semester. But that's the last thing that I needed in order to get to the conclusion that I've been teasing this whole video. All right, this is the fundamental theorem of invertible matrices. All right. You've dealt with a fundamental theorem before at least once. Prerequisite for this course is at least one semester of calculus. The fundamental theorem of calculus is the tool that allows us to evaluate a definite integral by finding antiderivatives, relates the derivative and the integral. There is also a fundamental theorem of algebra. Fundamental theorem of algebra is that an nth degree polynomial has n solutions if you include the multiplicity. The fundamental theorem of arithmetic tells us that every number has a unique prime factorization. The fundamental theorem of invertible matrices tells us when a matrix has an inverse. And it does so in a kind of strange way, right? The following statements are equivalent. There are about a dozen statements here. And when I say that the following statements are equivalent, what I mean is, if you know that any one of these statements is true, then all of the other statements must be true. And if you know that any one of these statements is false, then every other statement must also be false. All right, let's list all of these out. All right, that pretty well fills the screen. I apologize, I know it's tiny. You may want to look in your book and see this printed out instead of trying to read what I have scribbled on the screen, but I wanted to try to fit the whole thing. The linear operator defined by A has an inverse transformation, is equivalent to the matrix A is invertible, is equivalent to the linear system AX equals B has a unique solution for every vector B, which is equivalent to saying that the homogeneous linear system AX equals 0 has only the trivial solution. That's equivalent to saying that the reduced row echelon form of A is the identity matrix, or the nullity of A is 0, the rank of A is n, the columns of A are linearly independent, the rows of A are linearly independent, the columns of A span Rn, the rows of A span Rn, the columns form a basis for Rn, the rows form a basis for Rn. If we know any one of these things, we know all of these things. That is an amazingly powerful theorem. And when you think about the power of that theorem, how do we prove that? How do we prove that the linear operator defined by A has an inverse linear transformation is equivalent to all of these? The matrix A is invertible. If we know that, we know all of these. How do we get through all of that proof? And that's actually the more interesting thing here. Sure, this is incredibly useful. It's the fundamental theorem of invertible matrices. Several of these are going to be points that we use. Several of them are going to be points we never see again. And spoiler, we're actually going to have a second version of the fundamental theorem in a little bit that's going to introduce a few new claims into the list of equivalencies. But for right now, we have a lot. I'm not going to try to prove the entire thing just because I don't have anywhere near enough time. But what I want to show you is a technique, a procedure for proving that a number of ideas are equivalent to each other. Instead of having to show equivalence for every single pair, what I want to do is try to form one or several loops. If I can show that the first claim forces the second claim, forces the third claim, forces the fourth claim, forces the fifth claim, all the way down, and then to the last claim, if the last claim is true, then the first claim is true, then no matter where I am, if I know that the rows of A are linearly independent, and I want to conclude that the nullity of A is 0, I can just go, okay, from here I have that, I have that, I have that, keep going down, loop around to the beginning, keep going down, and eventually I get to where I need it to be. All right, so that's the idea that I really want to present with this, is that idea of closing a loop. If we know one thing on the list, we know everything on the list, and we can get there by just proving a sequence of dependencies. All right, again, I'm not going to do all of them, but I'll show you a couple. Specifically, let's take a look at statement 2, statement 3, statement 4. From there, I'm going to jump to 6, which is going to give me 7 pretty quickly. And I'm going to go from there to 13. And that's where things get a little bit interesting. From 13, I can jump back to 9. From 9, I can jump back to 5. And from 5, I can jump back to 2. So it's not the whole list. There's several points that I'm skipping, right? 1, and then 8, 10, 11, and 12 all get skipped over in this proof just for the sake of time. You can go back and you can create another loop that contains those ones, and it gives you the same kind of a result. All right. So if I want to prove that 2 implies 3, if A is invertible, then AX equals B has a unique solution. All right, so let's assume that A inverse exists. Then AX equals B. I can multiply on both sides by A inverse. And A times A inverse is the identity matrix. And I just solved that system. X is A inverse times B. Whatever vector B is, multiply it by the matrix, you get one result out, and you are good to go. Now let's take a look at 3 implies 4. This time I want to assume that AX equals B has a unique solution. For all vectors B. Then I can conclude that if I pick B equals 0, that's a special case. And we know that AX equals 0 always has the solution X equals 0. If it has a unique solution, that's the only solution. We're good to go. Now I said I wanted to show that 4 implies 6. So assume that 0, I guess I should say that X equals 0 is the only solution to AX equals 0. Then the nullity of A, the set of all vectors which are solutions to the homogeneous system, is the 0 vector. And as we showed not too long ago, or talked about at least, the dimension of the set containing just the 0 vector is 0. To show that 6 implies 7, well, 6 tells us that the nullity of A is 0. 7 talks about the rank of A. And we know from that lemma that I talked about and didn't quite prove that the rank of A plus the nullity of A must be equal to n. And if the nullity of A is 0, that means that the rank of A is equal to n. All right. From here, I said I was going to prove that 7 implies 13. Remember, 7 is that the rank of A is n. 13 is that the rows of A form a basis for n. Well, remember that the rank of A is the dimension of the row space. And the row space is the span of the n row vectors. And that's what we need. From here, a couple of other ideas. The dimension of a vector space is the number of vectors in its basis. And if we have n row vectors whose span is the vector space, well, then those row vectors must be a basis. The rows of A form a basis for the row space, and the row space is a subset of Rn. Well, the only subset of Rn that has dimension n is Rn itself. So the rows of A form a basis for Rn. And that's what number 13 told us was going to happen. All right, at this point, I'm going to start working backwards. I want to show that 13 implies 9, which is actually pretty straightforward. Assume that thing we just proved. The rows of A form a basis for Rn. And remember that a basis is linearly independent. And the only way for the rows of A to form a basis is for the rows of A are linearly independent. From this, I wanted to get back to 5. So we assume that the rows of A are linearly independent. And remember, number 5 is that the reduced row echelon form of A is I. All right. This is a claim that we've talked about, but kind of in its converse in the past. We've used the fact that if there are linearly dependent rows in the matrix, when you perform elementary row operations going to reduced row echelon form, you'll end up with a 0 row. Another way of saying that is that the only way for a 0 row to appear when performing elementary row operations is to have linearly dependent rows. And in our case, we have linearly independent rows. Since our rows are linearly independent, since the rows of A are linearly independent, the reduced row echelon form of A has no 0 rows. And the only square matrix in reduced row echelon form with no 0 rows is the identity matrix. So A must reduce to I in order for this to work. And then one last step. assume that the reduced row echelon form of A is I. The process we have for finding the inverse of a matrix comes down to put the augmented matrix up with the matrix we care about on one side, the identity matrix on the other, perform elementary row operations, get to the end where we have the identity matrix on one side and the inverse on the other. So from our process for finding the inverse of a matrix, A must be invertible if its reduced row echelon form is I. Right? The process we use for finding the inverse of a matrix succeeds only when the reduced row echelon form of A is I. So a inverse must exist. All right. And that closes our loop. Again, I know that I didn't include every statement in the fundamental theorem. I think this took long enough just with the ones we did. We could extend that out and add some more. But this is a pretty good place, right? We started at 2, we jumped around, we saw a bunch of other things, we got back at 2. So we have a loop of equivalencies. No matter where we start, we can continue through the loop until we get where we want to end up. Again, if you're really interested, you can see how you can create a couple of other loops building onto this one to include some of the other ones. The proofs are all laid out in our textbook. And in the next week, we're going to be looking at adding even more claims that are equivalent to all of these things. So things to look forward to. All right, with that, I want to wrap this video up. I'll give you a problem to try on your own. We'll go back a little bit and think about those couple of theorems that we skipped over in our earlier discussion. So we talked about the fact that the rank and the nullity of a vector space, if you add them together, you're going to get n. We didn't really show that, although we played around with it a little bit. So consider the matrix, and let's look at something that's not square, just to make things a little bit more fun. 1, 3, 4, 3. 3, 9, 12, 9. 1, 3, 4, 1. And using the tools that we've used in the past, I want you to calculate the rank of A and the nullity of A. Right. Again, not using the things we've learned anew, just using the vocabulary. Remember, the rank of A is the dimension of the row space. So you want to take the matrix, put it into reduced row echelon form, count the number of non-zero rows. The nullity is the solution set for the homogeneous linear system. So take this, multiply it by an appropriately sized unknown vector, set it equal to the 0 vector, solve the system, see what you get. If you think about it, you can kill both birds with one stone, but then check those, add them together, and verify that you get a number that's equal to the dimension of the vector that you would put in. All right, so play around with that, see what you get with it. I'll see you in the next video.